So thank you very much for giving up your evening. This evening, we're going to take a quick look at the tiny forest, and then we're going to go straight into our tiny forest tree survey campaign results. So that was held in October. So from the 12th to the 20th of October, we were encouraging people to go out to their local tiny forest and to invite people into their forest and to help us do some measuring of those trees. So from all across our network. So a reminder of what a tiny forest is for those that are already engaged, but for the new, like Dove, we'll just quickly explain. So a tiny forest is one of Earthwatch's big programs, so within the Nature in Cities. So a tiny forest is a dense, fast-growing miniature native woodlands, and so they are roughly 600 trees in the size of a tennis court. So that's about 200 meters squared, and so that's planting about about 3 trees a meter squared. So that's a lot more dense than you would see in a usual urban tree planting initiative. And that's because we follow the Miyawaki method of planting. So it's a particular reforestation method that was brought to us by Akira Miyawaki, who was a Japanese botanist. And he studied natural vegetation, and he studied pristine vegetation that was unaffected by human disturbances. And he noticed that actually those co-working ecosystems with lots of different species working together actually thrived. And so the method that he's developed looks at those pristine environments or those pristine ecosystems and brings that into a planting methodology. So what we do to plant a tiny forest is we include between 15 and 25 different species, and that includes all of the 4 different forest layers. So we've got our slow growing canopy trees, like our slow growing oaks, and then we've got our sub canopy, like the birches that will grow quickly because they're pioneer species, so they take off really quickly and change the environment for the other species. Then we've got some understory and some shrubby species, which will naturally grow faster and will occupy a different space within the forest. So we've got lots of different niches within the forest, and all of that competition between those forest layers helps with that immediate growth spurt and that growth rate, and that's what we're looking at in the tree survey campaign. And so we plant these tiny forests in urban areas where high quality green spaces are lacking, and so we call tiny forests an urban nature-based solution. So just a reminder of what the Tiny Forest Tree Campaign was and our ask to our amazing volunteers. So it was a week-long monitoring event across our growing network. We've now got more than 250 tiny forests all across the UK. We've got another 45 in the pipeline. So keep your eyes and ears peeled for more planting days coming near you. And so we were encouraging people to go out to visit their tiny forests for a mass data collection across the network at the end of the growing season, so that we can have that data at that same time. And so that was really useful for us to look at the growth rate for that year, and then to build in our database as well, to build our data set. And so it was a simple tree measurement survey. So we were getting people to measure the height of their tree and the width of the stem and how many stems they have. And that helps us work out the carbon stored and their growth rate. And we did do that at 100 different trees in the tiny forest. And those trees are tagged and they are representative of the forest. So they encompass all of the different species and all of the different forest layers as well. So we get a good representation of the forest and the species planted as well. And by you guys getting involved with this data collection and the citizen science monitoring, we are helping to fill that knowledge gap around the Miyawaki method and Miyawaki forest. So it's become more and more popular as a method, and it's springing up globally, which is amazing. But there's this gap or around the method, and so we don't have the evidence to support the method. So all of our citizen science is bridging the gap between that. And so we've got pictures of Whitney, which is our star, our first tiny forest. And so this is when it was planted, the summer that it was planted, and then we've got last season in the summer. So we can see that this is a colleague, and the trees are well beyond the height of my colleague. And that's only 3 years worth of growth, and it's grown even more. So it's truly impressive, just like the Hammersmith tiny forest. So that's what you've got to look forward to. And then I'm going to pass over to Kevin, who has been looking at all of your results, and he'll let us know a bit more about what we found and what it means.
Hi guys. So yeah, it was brilliant. In 1 week, it was like a huge amount of data that everybody pulled out. There was 501 trees and shrubs counted, of which there were 35 different species across 25 of the 250 tiny forests, which is like very good. That's really just a gigantic data set in 1 week. This is amazing. We have measured a minimum of 83 kilograms of carbon. I'll chat about it a bit more later, but we're pretty sure that there is more carbon than that being sequestered. But of what we have measured, we know that that's the minimum. And if you were to stack all of the trees on top of each other, it would be 7.2 Big Bens tall, which is like pretty incredible. That's everything that we measured just in 1 week, which was very impressive. Oh, sorry, Georgia, could you? I'm going to keep pressing the next button. Would you mind? Thank you.
You're good.
So the first figure is a map of Britain and Ireland, a little bit of France and the Netherlands in there as well. And the green dots are all of the tiny forests across the UK, Scotland, and Dublin. There was one, actually, now that I see it, there is also one in Belfast that's missing. So I'm going to have to figure out what happened to that one. But the second figure beside it is all of the tiny forests that were measured just this week. So it's a pretty good spread. It's not that all of the measurements were concentrated in one area. The most measured place was Cartor Park in Bromley. But it's really good that like there's a distribution. It's not everything was measured in one place. We got a good representation of quite a lot of the forests, which means we can use the data much more broadly. If we do the next slide. Sorry, Georgie, it feels really weird to ask you to do
You're
that.
good.
The three things that we found the most of were hazel, oak, and birch. They were the most commonly found trees in this week. The only thing we found one sample of was the wayfaring tree, which I found out was called the wayfaring tree because it was cool. Yeah, they're the most popular, most populous trees. But the wayfaring tree I found out was called that because it was only found, or it was very commonly found on roads and pathways. So that's how it got its nickname. And yeah, a couple of trees more common, a couple of trees less common, but still we got a good representation. We got a good diversity of species. 35 species across the whole thing means we're not just measuring one or two things, which is important. And then in the next slide, we have the heights. Alex, you were chatting about it is incredible when you start to see how fast they grow. The tallest that was measured across everything was in Birmingham, an ash tree, an aspen, sorry, and it was 5 meters tall. They're starting to form mature trees and form canopies, which as the forest grows, that's a qualitative change in the dynamics that happen inside forest. So we think that over the next couple of years, as they start to come into this slightly more mature stage, we'll see a lot of changes happen in the composition of the different insects, birds, and everything else that's living there, which is quite exciting. It'll be really good to watch and see what happens. and they have been growing incredibly quickly, which is amazing. So on the next slide, so carbon. One of the things that we measure is the amount of carbon that's sequestered in the trees. And why do we measure carbon? So carbon is an element. It's a molecule. It is an element, in this case, in the molecule carbon dioxide. So for every 3.6 kilograms of carbon dioxide, there's 1 kilogram of carbon because of the 2 oxygen molecules at the same time. Plants respire. They photosynthesize and then they respire. So they bring in sunlight, carbon dioxide, and water. They make it into the photosynthesize, and they sequester those sugars into their body. So this microscope picture here, the carbon is locked away. So a lot of the coal that people burn, that's trees from millions of years ago that just got compressed by the earth and stored up. So that same process, where the trees take in the carbon dioxide out of the air, bind it to their body, that stores carbon. And because we have the problem at the minute with carbon emissions, we're able to take carbon out and lock it away. And so long as we actually keep it locked away, we can start to make a progress towards helping to sequester carbon. We also know that the tiny forests do a lot of other things as well. They're important for biodiversity, thermal comfort. They're really good as community spaces, which is really important. So this is why we measure the carbon. And then on the next slide, it's how we measure the carbon. So what you guys are doing, this sort of set of equations, we know this number. We can estimate the weight of a tree broadly from its height and its shape. If you take the diameter and you take the height with a constant of 0.05, you can tell that roughly its whole wet weight is a certain number in kilograms. There's variation. Like, not all trees are the same height, not all trees are the same shape, not all trees follow that thing exactly. And one of the things we're going to work on in the next year coming is trying to do some research into, could we tailor that number? I know Claire was chatting about the idea of editing it for different species of trees, but we'll have to start somewhere and work ahead to it. Once you have the green weight, you can tell the dry weight. And just because of tons of experiments, people have done this heaps of times, we know roughly that the dry weight of a tree is half the wet weight, the green weight, and then the carbon in the tree is about half the dry weight. So when you measure the size and the shape of the tree, you can measure roughly how much carbon is in it. But I think one of the things that should come out straight away from that is we're not measuring the roots. We're not measuring what's below the ground. We're also not measuring a lot of the other impacts that the tree has. So we think that this is a minimum amount of the carbon that they have measured. But we're pretty sure that at the very least, that is the minimum, and it's probably more than that. So then on the next slide, how much carbon did we actually measure? So in 1 week, we measured 83 kilograms of carbon across the 25 tiny forests. That's the same as about 304 kilograms of CO2. And here you can see like the kilograms of carbon that were in each species. And it kind of makes sense because some of them were much more common than others. So silver birch was, if you take all the carbon that we've measured, silver birch had most of it. But that kind of makes sense because silver birch is really, really common. So if you try to account for which ones are the most common, then on the next slide, it's which individual species tended to have the most carbon. And on average, it was elders. So elder tree, it's not the most common, it's not the tallest, but I think probably because it is the biggest combination of height and width, then per tree, it's tended to have the most carbon sequestering, which I think is interesting. It'll be interesting to see how that evolves as the trees mature. Like you'll have the early successional, the early stage trees like beech and birch, they start off and they grow really quickly. Then, you'll start to have elders coming in, and then eventually we'll see things about like oak and all coming in. They'll start to like get into their own, which it's going to be really good to watch and see how this develops over time. And then on the next slide, These are the things that we have coming up in the next couple of weeks and months. So we have more tree planting happening. I know I'm going to a thing in Dublin in January, but there's a couple of different tree planting things happening across the UK. And you can follow on the Eventbrite to see what's happening there. This data that we gathered this week is going to go into the Tiny Forest report. So we've done a report for 2022 and 23, and we're currently working on the report for 24. And that should come out, or I don't remember which quarter it's coming out, but it's coming out in 25. It's coming out next year. And the other piece of exciting news was the Miyawaki Research Network. So, like Georgie said, there's been like the citizen science that's happening here is a lot of the research that happened on the Miyawaki and on the tiny forests happened in Japan and India because they were the first to adopt it. I think the tiny forests in Japan aren't tiny anymore. They're they're really impressive when you look at the photos. After I think 38 years of growth, the trees are incredible. Um, but Japan and India are a different climate to here. I think a lot of the early trees that came into the Netherlands, they definitely noticed like it works, but it's slower, and you have to, because we're a colder climate, it takes a bit longer for the trees to grow. And being able to say, this is what grows, this is the rate it grows at, these are how the different species interact, here's how we can protect endangered species and create habitat for them, here's how we can sequester carbon, here's how we can do this. Being able to say that reliably will be really useful. So the Miyawaki Research Network is going to try to help make a network to organize that kind of research. So there's quite a large group of people involved. There's Earthwatch, but it's also Leicester and Dundee, and there's a couple of French groups in there. It's like a long list of collaborators, but that's going to be exciting. So that's what we're working on in the next couple of weeks and months. And yeah, and then the next slide is just thank you guys for coming along. And if anybody has any questions or wants to chat, just let us know.
Thank you, Kevin.
I'm imagining I can just butt in and ask rather than putting my hand up with such a small audience.
Yeah, of course.
Thanks so much for that really, really exciting overview of where things are at. It's so encouraging. I'm disappointed for you guys that you don't have a bigger audience to share that information with. But I'm super excited. I hope you don't mind. I took lots of snaps to share it with the team because I can see that that Norman Park was fortunately participated, but unfortunately was the only tiny forest in Hammersmith and Fulham to submit data. But I'll share it back with the team at Norman Park. So firstly, to see, can I get your slides anywhere to share it back with our groups who couldn't participate, and maybe share the link from the recording so they can engage. But also to see how your report will compare with year-on-year data. Your 2024 report will look back at the changes over time, because obviously, Kevin, you were talking about having more data from India and Japan, just given the ages of those forests, and we're still in the early stages or growing stages, if you will. How do we see how the year-on-year stuff comes into play, and what we might be expecting to see over the next 3 to 5 years in our forests compared with forests in other locations?
Want me to start? Absolutely. That's why we're recording. So I can share the link, but it will, once we're done, it will go on our YouTube, so you can find it there and you can direct people there.
Awesome. Thanks, Georgie.
No worries. And our report will continue to look at all of the data collected over time. So we will look at the data collected from the oldest forests, from when they were first being monitored in their first year. And so we're looking at it over time, like you say. So obviously some forests now are going to have 4 years worth of data being collected over time. So they're now 4 years, and we've got 4 years to compare. But some of our forests, so the large majority, are in that 2 years stage. But again, it's all surveys will look at over time, not just focusing on this year. So yeah, we want to make those make it as useful as possible.
So I was just thinking, it was funny that you asked. I have the 22 and 23 reports open on my desktop at the minute. I was just working through them this morning. But yeah, it'll be cumulative, and it'll be exciting to see how they compare.
Thank you both.
Yeah, I just want to say thank you very much. That was really interesting. I learned a lot actually. It's good to see how much data you can get from the information we collect. I was really interested to see that. I thought one thing that's particularly interesting I noticed with this. Firstly, it's really good to hear that, like, you said, like, the estimate of the amount of carbon stored is probably a sort of more of a conservative estimate, which is really good for stressing what the potential they have is. Also, I thought it was really interesting that with the trees, there's the average in sort of like in terms of, like you said, it was about carbon stored things like birch trees and size. I noticed, I'm not sure if it's the same with a lot of the forests. I noticed our one particularly had a massive range, particularly the birch trees. You had ones that about 3 meters tall, and then others about a foot or so, depending on how well they've grown in the actual area. But that's interesting to see how that must be affecting the amount of carbon they're storing.
One thing that would be interesting to see would be the if a tree grows really, really quickly, is it like stretching itself like it's throwing heaps of stuff in? But if it grows slowly, then maybe it's like more compressed and more compact, so it takes its time, but it contains like sort of like a tortoise and the hare kind of a thing. One thing goes slow, but it stores carbon and moves a little bit, and the other thing goes, but it's a lot of like soft growth, and it doesn't store tons of carbon. It's an idea. Like people talk about it in other subjects, so it would be interesting to like do some studies and see. But
Yeah.
I chat to Georgie and Claire and the others in the team. We need to get the report, and then we start doing like all of the really exciting things.
Yeah.
There's lots of excitement about where it can go. Yeah, that's one thing we don't know. So obviously we use a constant, and we don't know whether the way, so obviously the Miyawaki method, the tree growth is so unusual, and that we're obviously using like equations that are for forestry, expecting the usual forestry growth rate. So yeah, it would be interesting to like further that and see. So having this like ongoing data collection over time at a good amount of forest is actually really useful to be able to see how the Miyawaki forests grow, and you can kind of map that, and we can then look at, well, do they follow this trend, and is there a model that we could better use to fit that, because it is so unusual, and the results, I mean, you can see on the ground, can't you, that you watch, and over the season they've leaped up. So yeah, it's interesting to see, but need to keep collecting the data to be able to see it in writing and through the numbers.
Georgie, how does that, I'm imagining that this data spurred a whole lot of new research questions, like the one that we were just kind of talking about. When the Earthwatch groups from different countries get together to talk about their local experience of the Tiny Forest campaign in their area, what does that discussion look like? Like, how do you take those results globally so that you can see that the impact of different climates has different impacts, changing climates have different impacts? How does that discussion evolve kind of on a global level?
So Earthwatch have tiny forests in the Netherlands, and so we get data through the same surveys, and we have that data from the Netherlands as well. So that's very similar, and those discussions are within Earthwatch. And I think that global comparison is one of the reasons why the Miyawaki Research Network will be so good in future years. So we have, like Kevin said, we have international partners, and we have recently been introduced to a contact that works closely with Miyawaki, Akira Miyawaki. And so that's how we've been able to see the photos and to ask her more questions about what they look like. And so I think that's something that will become more the collaboration and the sharing of best practices and all actually what does it look like and what were those problems at the station in your climate are something that we're going to have more and more as the research network grows. And the research network are working on doing a review at the moment, and that's across all of the different regions as well. So yeah, taking people's experiences into account as well. So yeah, stay tuned.
Gotcha. Exciting times.
Exactly. Yeah. And we've got some information about the Miyawaki Research Network on our website with all of the different partners. And yeah, updates will be shared through Earthwatch. But yeah, there's lots of partners and lots of people involved doing their own things.
So I have a question. You said that the most numbered species you had were hazel, English oak, which is also called pedunculate oak, and then you had the silver birch, right? When I looked at the tiny trees in your pictures, all those trees are really, really close together. And so I'm concerned about their survival rate of some of those trees, which some of them, like the hazel, love to be underneath those taller trees, the oak and the silver birch. They love that. But they also have their own cadre of insects and all the little biodiversity of each tree is totally different. And so, like your English oak is going to grow really tall, but then as it ages, it's going to get shorter. It's one of the few trees that does that. So you have these different levels in your little tiny forest, and I'm wondering how you are managing how they impact each other, because as they grow, you're going to have a whole bunch of different things going on there that may or may not support the life that the tree is best suited to support. That's just a general observation from how close the trees are together. I don't know a lot about trees except what was in the manual that I had to research to find out about. But I do understand that they need space, a little space. And you've got all the different lichens and fungi and all the other things that the biodiversity of the tree will encourage. And you've got these little space. And I think any planting of trees anywhere, even in tiny forest, is awesome. And there will be ramifications of having so many trees in a small space. So that was my question. If there's a question in there somewhere. I don't even know if there's a question in there somewhere.
No, it's good. Can I, George, do you mind if I have a go? And then you'll correct all of the nonsense that I say. I think a useful analogy is thinking about what happens in a forest naturally in ecological succession. Say you have like a large mature forest. You have a massive bank of seeds in the ground. And we know that seeds can last for at least 150 years. Several species, the seeds, they sit in the ground and they're able to persist for a long period of time and still germinate. From a couple of different studies that looked into that. The seedlings don't usually come up normally. The mature forest, it's a stable system. And then every once in a while, a big tree falls. And all of a sudden, you've got a change in the local microclimate. You've got sunlight coming in. And then every seed in that little square inch roars up. They don't wait. They just charge straight ahead. And most of them die. Like, eventually, 1, 2, 3 will make it into like a mature species, but they're used to the idea of growing with other multiple fast-growing trees. They're going to have to they will eventually naturally adapt to their density, and some of them will naturally thin themselves out. But the system as a whole mimics what happens in natural systems and becomes a stable, self-supporting system, self-supporting forest. That's the idea. Like in a lot of forestry and a lot of forest planting, people come along and a human being makes a decision. I will put this tree here, and it's the person making the decision. And we make decisions like it's useful to put them this many meters apart because that's useful to me. Trees don't do that. They don't have that experience. The trees, if there's a heap of them in one place and they're competing and supporting and interacting with each other and interacting with the mycorrhizal network underneath them, they can find the best spot for themselves and they can grow. You're taking the decision-making requirement away from the human brain and putting it to the tree and the mycorrhizal network. They figure out this is where to get a stable system. That's the idea. And it seems to work reasonably well in other climates. I know a lot of the tiny forests in Japan are coming up to 40 years old now, and they seem to be quite healthy and resilient. And I think the Indian tiny forests are quite old as well. But we'll just have to see how the ones in the UK adapt and how they grow as well. Georgie, what did I get?
Yeah, these are questions that we're asking, and yeah, like Kevin said, the forest will naturally thin out, and all of the different species that we plant are in, so they mimic that of a local ancient woodlands, and so the species chosen are native, well suited to the site specific, but we are using those species that are in a local ancient woodlands and looking at the proportion wise as well. So it's not loads of one species. Those species are interacting at different niches and different habitats within the ecosystem that we're planting. So we're not planting the trees, we're like creating the ecosystem, and there will be die out because there's more mortality, and that's something that again we're recording when we look at our tree growth survey. We're recording mortality as well, but these are questions that we don't know the answer to in our climate, and so we don't know, and the more they grow and the more we can see for ourselves, the more we learn, and we can answer these questions that everyone ask these questions, and it will be really interesting to see in 5-10 years time. Good question.
Well, I suspect it'll change over time too, because if you're looking at silver birch, which grows relatively quickly, or if you planted any other types of birches that grow very quickly, then the hazels are going to go under them and love that. But then some of those, like the river birch, it's going to be under, by the lowlands. And then others, like your peduncular oak, they like the drier soil. So, you're going to have them in different places. But maybe that the oak is going to grow really, really slowly, whereas the birch is going to grow really, really fast. And the hazel is going to be in between and saying, boy, I sure love this canopy I'm under. And then the canopy is going to change when the oak gets taller than the birch, right? And so you have, and it's slow growing. You had 3 years time, you had these trees about this far over your head. However, that's they'll change, because the hazel's relatively, that's a squat little guy. He's short like I am. But then the oak and the silver birch is going to be really, really tall, and they'll shoot up like a teenage boy, when in the growth spurt, when you can't buy shoes or pants for them because they're growing too fast, right? So we have that going on, and then meanwhile, here's oak, like a little turtle walking behind, steady as she goes, and jackrabbit birch is like boom right up there, right? And so I just think that you're going to have that. It's going to change. It's not static at all. What's going on, because you've planted them all at the same time, is going to change. So that's really interesting to see who wins, right? Who's actually going to win that race? Is it going to be rabbit or turtle? We don't know, right?
I love these analogies. That was brilliant. That was amazing. Yeah, exactly. You're so right. We don't know, and it's constantly changing. It was a good discussion. Is there any other questions?
Yeah, I have a question. Since we're on the subject and it just popped in my mind. By the way, Dove, I love that story and then the whole actions that you did. I think you're a great storyteller. Like boom. Yeah, my question was really a little bit related to the formula that you showed on the screen about the height and the diameter. So the only thing that I could see in the formula was the height and diameter of the trees, but I know that every species has a different carbon sequestering capacity. So how is that used in the equation, or how is that made, controlled for when you just use the height and diameter of the trees as a very generic equation?
Do you want to go?
We don't, broadly, is the answer. To begin with, we got this equation from I think from forestry in the United States. They had studied it pretty well, and over a couple of years, and it works for their system. So we started with, here's a thing we can work with. This works reasonably well, but in principle, that number, the 0.0577, that could be different for multiple different species. But we don't know yet what that number is. As in, I don't know what that number is. It's possible somebody else has done research on it, and we will try and figure out what those numbers are and plug them in. Or else maybe people don't know. In which case we can try and take our data and share it with. If I can write an email now and get 20 researchers who would jump on this data. But we can do some research into, could we put that number more accurately for different species. One of the things as well that would be really interesting, it's not just, is that number different for different species, like oak or birch? Is that number the same for a Miyawaki oak versus an oak anywhere else? Sitka spruce, for example, is commonly used in forestry, and it gets a bad rap because it's sometimes used inappropriately. But Sitka spruce is native to Scotland and the Scottish Highlands, and it would have a place in a natural forest. Does its growth rate, is it the same? Spruce, holly, ash, is it the same if they're in a Miyawaki or if they're in a normal, I don't even like the word normal, in a conventional forest system? It's not clear to me that the Miyawaki system is less or more natural. Are we mimicking nature, or is this a human invention? That's a thing we'll have to spend a lot of cups of tea and navel gazing and thinking over. But yeah, I would like to get that 0.05. I would like to get that figured out for different species, and Miyawaki and non-Miyawaki and different systems, and see how we compare to other systems around the world.
Well, I think that's going to change anyway, because depending upon the density of the tiny forest, depending upon the growth rate of the trees around it, it's going to grow at different rates. Like, it may grow better on the edge of a forest if it's a colonizer tree, then when it's standing by itself, than it would in the middle of the forest where there's trees all around it and doesn't get enough light, right? So it's not going to grow as tall, it's not going to grow as fast. And so I think that's going to depend on location, geography. It's going to be the density of the actual tiny forest itself. It's going to depend upon natural predators. There's so many different things going on there. That's my first comment. My second comment is, if you do any qualitative research on this stuff, you need to call me, because I am all over that. I want to do that. So I'm a qualitative researcher. Please call me. I can do poetry and all that stuff all day long, talking about your trees.
Noted.
No, brilliant, definitely. There's it's quite exciting. It's the same as well. Some species of trees are social. I'm blanking on the word, but allopacic versus allophilic, I think. Some trees like to grow when there's lots of other trees, even if they're not the same species, just like lots of other trees around them. They
Like
enjoy
hazel.
company.
Your hazel trees are like that. They love other trees.
And I wonder if like maybe like the allopath, the ones that I'm mixing up the words, but the ones that like other trees, maybe they grow faster in Miyawaki, and then the ones that like a solitary time, they grow a bit slower. Be interesting to see.
Yeah, that'd be interesting.
It's this kind of thing. This is. I'm already thinking this is going to be a column in a data set somewhere, and I'm going to like have ones and zeros for for like are they this or not this, and like yeah, I'm going to create a data set and like figure this out.
This is what happens when you get a bunch of researchers in the same room, okay?
Oh, it'll be brilliant fun. Cool.
Are there any other questions before we wrap up? If not, thank you very much for all of you for coming and contributing and saying your bit. It's made it a brilliant session actually. And there's, like you can see, there's lots still to come. So look forward to having our monitor report, and so that will have not only this this data, but all of the data from all of our other research topics as well. And then we've got the Miyawaki method, the Miyawaki research method going network even. Continuing to develop as well. So thank you very much for spending your evening with us. And keep your eyes and ears peeled for more tiny forests near you.
Thank you. Bye, guys.
Thanks so much. Thank you.
Chat to you guys soon. Have a nice night.
Really enjoy